Okay, my video yesterday didn't go very well because halfway through the lecture, my mic failed, or the connection of my headset to the computer failed. So there were two options: either I redo the video or remove it. It's still useful. But on the other hand, today I woke up and said, as I'm experimenting with these videos instead of writing papers, I should perhaps try once again what I tried a few years ago, and that's very short stuff focused on a specific topic. And so the topic of today is going to be SI units and kinematics, I call it, but it's going to be about the big questions, the reason why you are listening to me, and I'm going to talk about the concept of mass, and from there branch out a little bit to my worldview. Physics, what's real, what's not so real. I will talk about these questions: time, nature, space, and time, and also special relativity theory. So let's go for it. SI units and kinematics. Let me start. Kinematics. I found it a nice word in 1911, the very first Solvay conference, which sort of revolutionized classical mechanics, I would say, but I still think classical mechanics is valid. We just need to augment it with what was called at the time the La théorie des quanta. The title of the or the theme of the first Solvay conference was La théorie du rayonnement et des quanta, theory of radiation and the quanta. As you know, Planck's unit, Planck's quantum of action, was discovered when dealing indeed with spectra and a whole range of atomic phenomena, where we finally realized that nature is quantized indeed, but exactly how, that's the question. But so I'm using kinematics as a term, sorry, because they also talk a lot about, in theory, kinetic theory. So that explains the term kinematics, no more, no less. SI units very important. I think actually, all my rambling, all my papers, ultimately, if you understand the revision of the SI units in 2019, so that's quite recent, but it has been prepared for a very long time, and I think the teams and commissions and scientists that were behind it should receive a Nobel Prize, because they did away actually with the concept of mass. I show here the website. We have the second, meter, and the kilogram as a derived unit, and then ampere, coulomb per second, and then we have sort of these macro units that relate to macroscopic situations: temperature, a mole, how many molecules in a mole, and the candela is a special one. But I'm not going to talk about that because I said we're talking fundamental physics here, elementary physics, and so that's what we're going to do. So mass is no longer a fundamental concept. How does it work really in this revision of SI units? Basically, the second had been defined already for quite a while as the inverse of a frequency transition between two energy states of a cesium atom, so that radiates out or absorbs a photon with a certain frequency, and so that has been numerically defined, the second, in terms of that frequency. As you know, frequency is 1 divided by a second, so many oscillations per second. And oscillations, well, I'm not going to go into that, but yeah, it's very important to distinguish between orbital frequencies, like we have in matter particles, and linear frequencies, like we have in light particles, photons and neutrinos. So then there is the absolute speed of light, so you can also attach a numerical value to that, and if you have a value for the second, then you will have a value for the meter, because you will say C is so many meter per second. So once you have a numerical value for that, a numerical value for that, you have a unit for the length. And then Planck's quantum of action was also, they put a number on it, a very precise number, and then you have a force unit, of course, because so many Newton times meter times second, you have a not a natural unit for the force law, but you have a unit. So then you get the kg, the kilogram, the mass factor as a derived unit. So you could basically say, well, we don't need it anymore. We can measure everything, as I'm going to explain in a moment, in terms of through the mass energy equivalence relationship in energy units, which is mc squared. So we can use energy as the fundamental unit of what mass really is. And so what is mass really? I said there are two contexts. In kinematics, the micro thing, what I'm talking about here is it is a measure of the inertia to a change in the state of motion of a particle, and a matter particle. And that's what I explained in previous videos. You know, I have these mass without mass models of, well, the two elementary particles that are stable, an electron and a proton. We'll talk about how the energy experiments. And we basically think of them as, you know, a point-like charge, Zitterbewegung charge, or Schrödinger charge, or whatever you want to call it, a naked charge inside of the electron and the proton that whizzes around at the speed of light. So then we have a model for the electron, from which we get the radius, plainly from the mass energy equivalence relationship, from the Planck-Einstein relationship, and then interpreting c, the velocity of speed, as it whizzes around. We can write that as a radius vector times a axial vector, the frequency vector. For the proton radius, I said you get like more bang for the buck, because for an electron we think it's an oscillation in 2D. For the proton we think of a 3D oscillation, and so the energy per radian of the frequency is 4 times h, and that's, as I said, just the factor that you have in the surface area of a sphere as opposed to the surface area for a circle. I'm not going to dwell on that. You can, of course, you get this formula. What I want to point at is that, yeah, A is a radius. We can vectorize it. It will require us to write Planck's quantum of action as a vector too. And, you know, C is a vector, and then, you know, we must get a vector. So we can write it as a cross product from Planck's quantum of action, reduced Planck quantum of action, times C. It must be a cross vector, not a dot product. A cross product, not a dot product, because yeah, we want to get a vector out. Writing Planck's quantum of action as a vector is sounds outrageous. You may never have seen that, but just like the frequency vector, yeah, h is also the unit of angular momentum, and we know we can represent angular momentum as an axial vector or a pseudo vector as well. It has a certain magnitude, but it's also directional. Things go around in a certain plane, and so the actual vector that measures its angular momentum or captures its angular momentum will be perpendicular to that plane. I'm digressing too much already, so let me clean up my sheet. I don't know why it's not working. Oh yeah, clean up everything that I wrote. It doesn't go any further. So yeah, mass is a concept that we no longer need. But you will say, of course, mass has a second aspect when we think of the fact that mass attracts to the force of gravitation. While gravitation is a pseudo force, and that's where Einstein's general theory of relativity comes in, which is a bit of a misnomer, I think, because it's not another relativity theory. It's really about the structure of the universe, and we think of it as having a non-Cartesian structure. And so Einstein's fields equation, you can read about that, has in them the gravitational constant and we use the concept of mass, but as we know, energy has an equivalent mass also. You need to integrate that in the dark energy and normal energy and electromagnetic fields. They have an equivalent mass. And so my point of view is a bit that if we would rewrite these equations substituting mass for energy, we actually wouldn't need the mass concept at all. Of course, it is useful in analytical situations. Let me go to this here, what I often show is, if you ask what is really like absolute, what is the essence, we'd say it's charges, moving charges or static charges, it's electromagnetic fields, and that's it. And in those, when we describe the motion of charges, and when we describe how electromagnetic fields generate or influence the motion of charges, then we have these constants of nature that do not depend on a reference of frame of reference, speed of light, Planck's quantum of action, and the elementary charge. So that would be the real thing, but I said this is a bit of a philosophical discussion and I don't want to be dragged into these things. What's more real, the speed of light or a charge? Well, it's two different real things. A charge is a charge and speed of light is the speed of light. What's relative is what is relative less real? No, it's just relative means that it depends on our frame of reference, but time and distance, um, they're real. And I mean, you can be very philosophical, but they're sort of inherent as we think of, we speak about charges in motion. Well, a charge goes in a certain direction on a certain trajectory and it covers a certain distance in a certain time. And so the way we're going to measure time and distance is going to depend on our frame of reference. But as said, it's as real as the idea of motion. Is the idea of motion real? I think it is. Two observers can agree when they are on the same stationary or inertial frame of reference that there's a charge there and it's moving in that direction. So that's a real measurement and a real thing. I said mass, force, energy, momentum, they're also real. Mass, it's not because it's a derived unit. We can always express it in energy terms, but it's a scalar quantity. That's real, and I said you combine these two, and that then forms our representation of the world. I would say these physical equations, Maxwell's equations, the Breuer relation, the Planck-Einstein relation, Schrödinger's equation. I write about it in my paper. I think it really does describe the motion of a charge in a field that is generated by a positive charge in some center in the hydrogen atom, but we can also have Schrödinger's equation in free space, and I explain that. And so my worldview is very simple then. It is basically what Wittgenstein wrote in his Tractatus Logico Philosophicus. Die Welt is one, and it's die Gesamtheit der Tatsachen, nicht der Dinge. What does he mean with that? We're talking facts. Tatsachen are facts, and Dinge is that's a philosophical category, and it can mean anything, a definition of something, an equation, a charge, or whatever. We're talking facts, and that's our reality. This probably does not make all that much sense, so I'm not going to continue to dig into that. The big questions that you have based on this very short introduction is probably this. Mass, okay, we say it's useful, at the same time derived. Can we associate a directional aspect with the concept of mass? I raised this question a bit by accident because I'm here in a discussion, and I'm not going to show that too much because André Michaud, a fine physicist, he's a bit reviving that, everybody's going back to Einstein's paper in the end, and this is the 1905 paper, written originally in Germany, and the English translation is not great, but if you want to look it up, you have the from Formula. At the end of his paper, he does talk and play and toy around with this idea that an electron, he confuses, just like Schrödinger and Dirac did, an electron with the naked charge inside, which is kind of sad, but where is it? He talks about the longitudinal mass and the transverse mass of an electron, and that kind of instinctively makes sense. You know, if an object heavy, an electron not so heavy, is moving in a certain direction, it's kind of you know, the force law. We have the force law, the force that we exert on an object will be equal to the mass and the acceleration, which may be a deceleration that we give to that particle. And we know if it's already moving a big truck on a highway, you know, it's difficult to slow him down in the direction of motion or to speed him up in the direction of motion. You need a lot of force for that. But you know, moving its direction of motion when a car hits from the side or something, that's fairly easy. And so that gives the idea that maybe, you know, when we talk about mass as the inertia to a change of state of motion in an object, that maybe there's two different mass concepts. I don't agree with that. And that's a bit what the discussion on ResearchGate is about. But you know, you can only write so much and talk so much, and I prefer to address it here. He abandoned that concept. I said if you talk about inertia, you're not going to talk about inertia in this and that direction, or maybe you will do that. It may make sense, but it's not in the concept of mass itself. It is in the very classical definition of momentum. The relativistically correct formulation of linear momentum is that it's mass, I said that's a scalar, times a velocity, which is not a scalar, that's a directional quantity. So the directional aspect of you know, an object having a lot of linear momentum in one direction and zero in another direction, and therefore you know, we can give it some linear momentum in another direction perpendicular to its motion or in some other angle to the line of motion. That's going to be easy. But so mass is not a directional concept. So I want to get clear on that, because that's Einstein played with that. I don't know if he revoked it, but he forgot about the concept later. It never popped up again. And so anyone who claims that mass is has a directional aspect, I think it doesn't show in the formulas. And sort of going back to what Einstein said or wrote in the latter years of his life, you have some discussions going on that. Doesn't make much sense to me. The other thing is then related to the second aspect is this gravitational constant. Can we like relate it to other constants of nature? There's a lot of research going on there. I mean, a lot of, but that's sort of for me pseudoscience or popular science that we say, oh, the gravitational constant, we should be able to link it to, you know, the elementary charge, to Planck's quantum of action, perhaps, the speed of light, you know, these fundamental constants of nature, which I showed just before in all these absolute um, quantities with a very specific physical dimension. H Newton meter second, c is a velocity dimension, q is in Coulomb. Yeah, of course you could do that, but then you would need you know, the general theory of relativity is how a certain distribution of mass and I would say a certain distribution of energy to include the energy of electromagnetic fields, which have an equivalent mass. Yeah, if you would define some standard distribution of that energy, say the energy in an electron or a lithium atom, I'm just or a water molecule, the Earth, or our universe, or not our universe, but our you know, a galaxy or something. But that's a meaningless exercise, and the relationship that you will find between your gravitational constant, which then is sort of normalized in terms of the standard distribution of energy, is well, yeah, you have that, but I said it's a rather meaningless exercise, and it all depends. You know, the result you're going to get depends on this distribution of energy that you are considering in your quest to relate gravity to the other constants of nature. I said gravity fundamentally, that's where I'm really a fan. Everything that Einstein said or wrote, he was right. So the gravitational constant explains the structure of the universe. As you know, then it's a matter of belief if the structure is closed. I think it is. It's spherical-like. That's what we see. It's a non-Cartesian structure. There's measurement, it seems to be expanding, strangely enough, expanding ever faster. The visible and real horizon of our universe in which we live is defined by the speed of light. We cannot see beyond what came to us in terms of gravitational waves or normal waves or radiation. When our corner of the universe, which may be the whole universe, was born. But the fact that the universe seems to be expanding ever faster, suggests maybe that there are other universes around us, but they are part of the same universe, of course. In any case, you have a geometry there that explains the gravitational constant, and the other way around. The gravitational constant explains this non-Cartesian structure of the universe. So again, that's discussions I want to close for myself, and questions I get on that is just like I don't entertain them. Gravity is a very different beast than the one and only force I believe to be present in the universe, which acts on an electric charge. We have found no other charges. There's no color charge or a strong charge or whatever. So weak forces, strong force, nuclear forces. No, you can explain them in terms of electromagnetic forces and fields acting on charges. So that's it. How can we explain then, this is the sad thing about the video that went wrong here, dark matter and energy. Well, what I wanted to point out, but then the sound went dead, is that the electric force, as we know it, is right-handed. If you have a certain convention for determining the orientation of your x, y, and z axis in space, and you have a convention for, I like to use the imaginary unit as a rotation. I rotates your real axis into the imaginary axis, and x-axis into y-axis, and it rotates it counterclockwise, of course seen from a certain direction. Standing in front of a clock and standing behind of a clock will determine whether you see time going clockwise or counterclockwise. And so, but if you respect sort of conventions, you have conventions for all the mathematical symbols in your equation, you will still find that the electromagnetic force, according to these, is right-handed. The magnetic field vector follows is perpendicular to the electric field vector. Perpendicular means there's a difference, an angle of 90 degrees, but it's a negative angle. And of course, if you look from the other side, it's a positive angle. So right hand, left hand again, you need to have firm convention on that. So what I think is that we can imagine, and this is really, I think, my most nonsensical paper. It's also one of the shortest, where I imagine, like, just what Dirac found when he wrote down his equation, the Dirac equation for the motion of electrons, which argue in a paper. I think it's Schrödinger's equation is the real one. There's inconsistencies in Dirac's one, but I'm not gonna delve into that. That sort of stuff you need to Google. Look at my interpretation of the Bruce wavelength as an orbital thing, and a lot of other stuff. But I think, Dirac found that there was a mathematical possibility to, sort of redefine and everything based on, instead of a negative charge, a positive charge. So that's where he said, antimatter should exist, a positron, and then all other things. A proton has an antiproton. We can define an anti-atom, an anti-molecule, and but I'm not talking about matter antimatter here. I'm not really talking about charge symmetry, as it's called in physics. You put a plus sign where all your minus signs were for the charge, but you put a plus sign in front of this equation here, and you say, like, well, we can imagine a left-handed electromagnetic force, and it would also yield a completely feasible world, I would say. And as we do not have a clue about an estimated 80% of dark matter, dark energy we cannot see in the universe, but we think it's there because exactly the fact that we can measure the curvature of space, we can see gravitational effects in action, and there's a lot more matter and energy from what we see, you know, the motion of universe, of galaxies, sorry, and stars. There's unexplained matter there, and we can't see it. It doesn't send out any radiation. Well, I think it does, but it's radiation that obeys, you know, maybe a left-handed force, and so it's not going to interact um, with our world, matter and antimatter. As you know, matter and antimatter annihilate each other. I'm going to say a few words about that, what really happens or might be happening. I'm a bit skeptical about that, but it's not a violent matter antimatter encounter. No, we know it's there, and it doesn't interact at all with our world. And so that's the hypothesis I explained yesterday briefly before my sound got cut off. The ultimate question for me, and I'm gonna stop my, is this indeed matter and antimatter? I'm not talking about dark matter and energy anymore, but just like, okay, you have an electron and a positron coming together. I said in our models, we have a mass without mass model. We have a negative charge spinning around at the speed of light, and in the positron, the other thing, it spins in the other direction if its magnetic moment is oriented in the same way. And we think when a positron and electron come together, you know, first they will probably line up their magnetic moments and make for a much stronger magnet as they come together, and the field lines of both combine in what I show here. A very strong, a magnetic field that is twice the size of the magnetic fields of the electron and the positron taken separately. So, but what you're going to have, they're going to really just probably, I mean, this is a big question mark here. What I imagine is that, you know, yeah, they just go and sit on top of each other, the electron and the positron, and we have these two charges here, opposite charges, and they must collide. When they collide, the theory is now that they will annihilate each other and they send out two gamma photons. Or gamma is got a symbol for a photon is gamma. So the gamma we're right. It's not a, it's a yeah, a gamma ray, a photon of a gamma ray. That's the theory. I think the jury is still out that that's what happens. My theory is a bit what I imagine is just one of the possibilities is that we that these charges don't get destroyed, but have that situation that is, yeah, in my mass without mass model of what an electron and a proton actually are, impossible. A charge that doesn't zitter around and creates an electromagnetic field that, you know, keeps it in place, and, you know, is therefore stable because it respects the Planck-Einstein relationship and Maxwell's equations. Now, maybe we have that charge going linearly, so it would be like a zero energy state. Well, not because it has a relativistic mass. We think half the electron mass or half the positron mass as it acquires the velocity of light, as it's photon-like. And at the same time, somehow, the other half of the total energy that was here, the kinetic energy in those two charges and then the energy in the electromagnetic field, somehow they must carry something of that too, but it's a particle that can't exist, or I think it can exist for a very short time, and I think these might be these heavy bosons, but bosons is you know, bosons can sit on top of each other, charges can't. Well, they can when they annihilate here apparently. Or maybe not. I said this is highly speculative. I would think that maybe we have a pair of W plus minus bosons that are that is being created here. You know, massive things because they have massive energy. The photon-like, they move probably at nearly the speed of light. They carry charge, and yeah, they must also be carrying sort of the dependent of you know, the kinetic energy that is in a charge is electromagnetic field. The electromagnetic field here sort of vanishes, so it must go somewhere, and it probably travels with this. I mean, that's my wild hypothesis. It travels with these charges. So I think the judge is still out on whether what I write here, the Dirac hypothesis and the Bright-Wheeler, that's the reverse. Dirac process says indeed there is this annihilation charge somehow magically becomes a field. Traveling field, traveling electromagnetic field, two photons. I don't think charge gets lost. The Bright-Wheeler hypothesis is the reverse. There's no conclusive experiments on that. High energy photons are made to collide, but there's always like, a nucleus in the background or something else, and an electron beam. And so I think there's sloppy accounting there, and the charge goes somewhere and comes from somewhere in these experiments. But that's in my humble opinion. Only this is really a minority point of view, but I think yeah, that's the one question I have. Not gonna be solved. Maybe the Chinese will do it as they're building accelerators and detectors like CERN has, but 4 or 5 times the size. And they're gonna redo all of these experiments, and I hope they come up with a more realistic theory and a confirmation of what I write here. Charge doesn't vanish, not in high energy physics, not in low energy physics, and not in high energy physics either. So the one thing we can say is that all these unstable exotic particles that have been discovered or hypothesized, should I say that, in the past 50 years, since the 1970s, come out of high energy interactions. And I think these high energy must somehow carry away not only the energy in the electromagnetic fields of the incoming particles, but also their charge. And maybe that leads to neutral particles, plus and a minus. But my hypothesis is a bit neutron is some combination of positive and negative charge. So exotic particles that have zero charge may also be neutral, because this positive and negative charge in them, and unit charges, not quark charges. So, but what characterizes that, of course, is that they are these exotic, and they do not respect the Planck-Einstein relation. And you may think, like what I write here, do they respect Maxwell's equations at all? I think Maxwell's equations must always be respected. But as said, we don't know. What I do know is that any combination of charge and electromagnetic field that it generates or carries with it must to be stable respect the Planck-Einstein relation. And so we're talking about disequilibrium states here, and these are very, very hard to model properly. I have a paper a bit on S matrices, and I said for an electron we can really represent it by an elementary wave function, an oscillation in one direction times another one, and this really gives you the x and y coordinates of your charge going around. In 3 dimensions, it's for a proton a bit more difficult. I explained it in the video, the problem of finding the equations of motion when we also have an oscillation perpendicular to the plane of what a charge would do, what the Titterwegen charge would do in an electron. And that's really it. Let me clean up my sheet and close this lecture. And now I really gonna. My girlfriend's coming back tonight from China, and I need to get back to, my day job. So I hope you enjoyed this, and it's only half an hour this time, and that's it. I just gonna quickly do show for those who are interested in it. This is the crazy paper, an anti-force to explain dark matter and dark energy. When I wrote it and when I published it, it does not have a lot of reads, I think. Yeah, rightly so. It's a bit chaotic. It's crazy. It talks about CP symmetry breaking. These symmetries that and symmetry breaking rules that come with them, which I think are a bit nonsensical. But yeah, about these characteristics that an anti-force would have. Very superficially, I haven't done much research on it because I thought it was a crazy hypothesis. But now, 2 years later, or more than a year and a half later, I think that this is the only sensible explanation of dark matter and dark radiation, because it's 80% of the matter in the universe. We already have such a mess explaining matter in this world that we know. So with all these strange quarks and gluons, whatever, and so I think if we can have what Dirac felt, an exploration and apply Occam's razor, say what are really the fundamental symmetries and asymmetries in nature. And thinking about the electromagnetic force, well, that's the biggest, almost blatant asymmetry in nature, I would think. We can have a set of Maxwell's equations, and we can reverse a minus sign, and now we get a very different force. And there's no reason to think it will interact with ours, because it's electromagnetic field vectors, the bivectors that you need in the geometry of these things. They just don't coincide with the EM bivectors of our photons and the electromagnetic fields that are generated by the charges in matter particles in our world. So you would have not a parallel world, it's here, but a world that doesn't interact with ours. And that's it. I wish you a very nice day.